Okay, hello everyone. This is session 4A. My name is Minsoo. I'm the session chair here. And let's see. We'll get started with the first presentation. Let's see. Okay, so our first presenter, Yichi, received his bachelor's degree in microelectronics from Tsinghua University in 2022. He's currently working towards a PhD degree with the School of Integrated Circuits at Tsinghua University. His research interests include reconfigurable computer architecture, domain-specific accelerators, and computational genomics. So, Yichi, whenever you're ready.
There has recently been a new paradigm shift in the field of computational genomics. So previously, data scientists tend to represent a DNA as a sequence of nucleotide bases. But as everyone knows, that the genetic variations are everywhere. So it is not enough to use a sequence as a representation. So in pangenome era, or we use something called genome graph or pangenome graph, where we annotate the original sequence with some local branches, which represents the genetic variations. So a real genome graph would look something like this. So it's not exactly the same as some genetic graphs. Well, as a computer scientist, we are fully aware of what graph data structures and graph processing workload would take to our computing systems. So it would be detrimental to the overall performance. So the problem here is that how can we mitigate the graph processing overhead, or how can we reduce the graph processing overhead? So in this paper in Harp, we leverages a property called quasi-sequential characteristic, which means those genome graphs, they somehow looks like a sequential structure, and we leverages these similarities to reduce the graph processing workload. Well, let's begin with a pretty simple example to showcase our idea. So suppose you are trying to find the distance between vertices, and you are handling a graph, then you need to some like graph searching or graph traversal algorithms. But if you are handling a sequence, you can simply get the distance by subtracting their indices, right? So the sequential version of the algorithm is much more simpler than the graph version. So when we are dealing with the quasi-sequential genome graphs, we can either make quite exact approximations by using the subtraction method, or we can employ some lookup table tricks to get exact results without doing the graph traversal. So we can access some like on-chip scratchpad memory or lookup tables. So here's our motivation. So in the past, the read mapping cores or read mapping accelerators, they need to go off chip to the DRAM to access the genome graph when there's graph operations. But now in Harp, we want to build something called optimization center and some on-chip SRAMs. And whenever there's a graph operation, the accelerator tells the optimization center, and the optimization center will decide whether it's a quasi-sequential or fully sequential like request, and it will become like on-chip accesses and on-chip calculations. But for rare cases where the graph is so complex, it will go back to the DRAM to access the original genome graph. So this is our motivation, and this is our guiding idea. And now the problem comes to two. The first one is how to make an on-chip representation of the structural characteristic. We want to make it on-chip because we want to have like real-time or very quick access. And the second one is how does read mapping accelerator benefit from these, tricks and strategies? So let's begin with the first question. Here we leverages a kind of graph motif called superstructure. We can see a superstructure as shown in the blue regions, like they are subgraphs with only two boundary vertices and in entrance and an exit. So for example, in here we have an entrance vertex and an exit vertex, and there are no other edges connecting from the inside subgraph to the outside world. So they are kind of an isolated subgraph. And those superstructures have a kind of nesting relationship, like those two blue superstructures, they are nested in these larger green superstructures. So when we eventually analyze the entire genome graphs, we can build a superstructure nesting tree. I say it's a kind of tree style thing, but it's not enough because it will still takes like 100 or so megabytes. So we cannot put it on chip right now. So in Harp, we introduce another strategy called pruning, or it can be seen as losing compression, that we get rid of those, leaf nodes, some of the leaf nodes, the small ones. Yeah, and it can effectively compress it into like a few hundred of kilobytes or some megabytes, and it can be placed on chip. And another good news is that accessing the tree data structure is more hardware friendly than accessing a graph data structure, because if you want to do some bottom up tree searches, it will be like, go through a linked list or something. But if you want to do the graph traversals, it will be far more complex. Okay, so here's a real use case, because so let's take distance calculation in graphs as an example. So suppose we are trying to find out the distance between vertex number 2 and vertex number 20. We first find which superstructure they are nested in, and we go all the way upwards to their ancestral superstructures, and we'll record their distance from themselves to the boundary vertices, which is the entrance and exit of their ancestral superstructures. And finally, the distance can be acquired by simply we add those distances together, and we can acquire the minimum distance between those vertices. And all this process happens on chip. So it will be good. And the second question is, how does read mapping accelerators benefit from this? So I wouldn't delve into more details about read mapping, but in read mapping, it's essentially something look like this. So if you want to make some DNA or genome analysis, you need to first prepare your biological samples and put them into a sequencing machine. The sequencing machine will split your DNA into many, cut it into many short pieces and generate some digitalized DNA fragments, which we call reads. So if you want to perform some downstream analysis, you need to put those pieces back together to reconstruct your entire genome. So this process is called read mapping. So they are essentially some approximate string matching algorithms, and they are the performance bottleneck. They are widely acknowledged as the performance bottleneck in the entire pipeline. So in the read mapping algorithms, we have two stages, which was called filtering and alignment. They will involve some kind of graph operations, that graph traversal stuff. And for the filtering, algorithm, it essentially does this kind of mathematical equation. It's an one-dimensional dynamic programming. And so we design a systolic array to accelerate and parallelize the computation process. But within each iteration, there is a distance calculation. It's a kind of graph operation or graph traversal operation. So each processing element in this systolic array is coupled tightly with an access interface to the Harp tree, which is the on-chip thumbnail I mentioned above. And they are tightly coupled to perform the inner loop like distance calculation. And for the alignment stage, it is another dynamic programming algorithm. So we also designed a systolic array, but the difference is that it does not have some graph operations in the inner loop, but rather the data dependencies in this dynamic programming are defined by the graph edges, as you can see here. So this would be a graph, and if we have an edge here, the data dependency in this 2D dynamic programming would look like something like this. So yeah, here we need some buffers to store those non-local data dependencies, and we propose several different mechanisms. So for the close range dependencies, which are dependencies shorter than 16 distances, we'll use some registers for each of them, and we call them local max registers. And for mid-range dependencies, we'll use some CAN-like or some small caches. And for long-range dependency, which crosses the boundary of a tile, we can make some new derived tasks. Like, for example, here's a tile, and here's a long hop from another tile to this one. We'll derive two separate tasks and then some gluing logic to combine them together. So these mechanisms can be enabled or disabled dynamically, which guided by the Harp tree metadata. So we can dynamically save some clock cycles and save some energy. So the entire acceleration system looks like this. So this is the Harp tree data structure, which is the like optimization center. And we have one filtering accelerator with 8 alignment accelerator to balance the overall throughput. Well, our evaluation was done for with human genome graphs. And yeah, we use some simulated read data sets. And we build our RTL, which was written in Verilog. So we have both RTL simulation and software model. The software model was for some more larger test cases. Well, for the whole system, we simply use an analytical model because those like acceleration tasks are invoked like in a coarse grain style. So there are no complex inter-task dependencies in there. So we simply use an analytical model. We compare our work with the state-of-the-art hardware, which called Segram, and also some commercial software packages like GraphAligner and MiniGraph. So yeah, here's our evaluation results. So the Harp is an quite lightweight design because we only takes 8 square millimeters chip area, and we have more than 20x speed up over the state-of-the-art hardware accelerator. So this is the speed up breakdown. I'll not delve too deep into it. So if you are interested, please check out our paper. And the final accuracy would be comparable to the software package, to some commercial software packages. And yeah, here's the final takeaways. So in this work, we build a software and hardware co-design that accelerates sequence to graph mapping, which is an important workload in pangenome. Yeah, and we leverage the quasi-sequential characteristics to efficiently reduce the number of graph operations and optimize the overall throughput. There are still several limitations, like the construction involves many empirical parameters and hand tuning, and we only tested on human genome graph, but I'm not sure whether it will be as effective as this for some other species, like if they have more complex genome graphs. But for human genome, I think it's okay. And that's all for my presentation. Thank you.
Any questions from the audience?
Hi,
Hi,
nice to
it's a
meet you
great
again.
work. Yeah. So I wanted to ask something. So I saw that you were doing some kind of pruning of the leaves when you were explaining your tree structure, right?
Yeah.
So like, I just wanted to know, like, does it lead to some loss in accuracy?
Yes, of
Uh,
course.
mhm.
I have some backup slides here. Oh, sorry, I didn't put that. So you can go refer to my paper, and I
Mhm.
in one subsection I discussed. So
Mhm.
what's the side effect or downside of the pruning? So it will cause some inaccuracies, but we think it's acceptable. Yeah.
Okay, so and like, is there a way to recover those accuracies? Because for some of the biomedical applications, a loss of accuracy might not be acceptable. So do you
Yeah,
have
but
some ideas about that?
so I think because we still preserve the original genome graph, it still stores in the DRAM. So if we think this operation will cause too much inaccuracy, we'll fall back to the DRAM, access. Yeah. Thank you.
John Demi, Microsoft. Have you looked into mapping this to an FPGA?
What?
How well does this map to an FPGA?
We didn't test it on an FPGA, but I think it's okay.
Okay, why didn't you?
So why are the concerns like it would not map to or not efficiently map to
Yeah,
FPGAs?
and I'm just wondering why you didn't come up with an FPGA implementation of this so you could actually run it.
Yeah, I'll try to, but actually we are trying to tip it out recently, so we are doing the ASIC design flow.
Okay.
So probably later on we'll try FPGAs.
Yeah, I just want to point out that this type of application is what we
Mhm.
call long tail.
Uh-huh.
It's what we call a long tail application, so it
Okay.
may or may not justify making an ASIC for use in production, and FPGAs are a great use for
Oh,
that.
I see. Thank you for the
This is
tips.
gonna be my question for all of the accelerator papers.
Thank you.
Let's thank the speaker once more. Okay, next up we have GSCore. The presenter is Junseo Lee from Seoul National University. Junseo is a third-year PhD student at SNU. His research interest is in architectural support for emerging workloads, particularly graphics tasks such as neural rendering in mobile and edge computing platforms.
So thank you for the introduction. Hello, everyone. I'm Junseo Lee from Seoul National University. Today, I'm going to present our work, GSCore efficient radiance field rendering. I'm sorry. So hello, everyone. I'm Junseo Lee from Seoul National University. Today, I'm going to present our work, GSCore efficient radiance field rendering via architecture support for 3D Gaussian splitting.
Okay. Let's try again.
So I'm sorry. So hello everyone, I'm Junseo Lee from Seoul National University. Today, I'm going to present our work, GSCore Efficient Radiance Field Rendering via Architecture Support for 3D Gaussian Splatting. So what is 3D Gaussian Splatting? It is an emerging technique that generates photorealistic images using a set of Gaussians.
Sorry about that. What we're going to do is we're going to let the third speaker go first and let him use a different laptop.
Okay. Oh no, we do not need. Okay, let's see. Oh no, we do not need audio. Oh, just the video is okay.
We need to record it, so you have to plug it in.
We need to record it.
Yes, we are recording it there.
So this,
Yes.
yeah. Okay. So let me go first.
All right, quick introduction on the third speaker. So Ruihao is currently a fourth-year PhD student at the Institute of Computing Technology, Chinese Academy of Science. He's supervised by Professor Guanming Tan. His research interests include domain-specific architectures and RISC-V for high-performance computing. Take it away.
Okay, thanks. And now let's begin. Good morning. I'm Ruihao from SAT KAIST. It's my pleasure today to share with you our new data compression accelerator, BeeZip. This is my outline today. And now let's start from the background. Nowadays, our computing systems are filled with massive volume of data from multiple scenarios. Data compression is a technique that can help us shrink the size of data without losing valid information. The shrink of the data means the cost reduction of storage and bandwidth resources. We measure the performance of the data compression algorithm by two metrics, throughput and compression ratio. Throughput tells us how many bytes can the compressor take in per second, and the compression ratio equals uncompressed size divided by the compressed size. Both of the metrics are as higher as better. Keeping this guideline in our mind, we find out that this standard is a rising star among these commonly adopted compression utilities. It's a balanced improvement in these two metrics. Thanks to these improvements, this standard is becoming increasingly popular in critical scenarios such as data centers, operating system kernels, and so on. Our goal is to further improve the throughput of this standard while maintaining the compression ratio, making it more suitable for the era of big data. Before we dive into the accelerator design, I think a quick start to compression algorithm is necessary. This standard is based on LZ77, 50 years of classical compression algorithm. The story of LZ77 is about performing substring matches on the sliding window. We shift the data into the sliding window, then we try to find the longest match of the height sliding window into the history sliding window. For this example, we have 3 potential matches and we choose the longest one. We can just take down the offset and the length of the match, and the redundancy in the data is eliminated. Of course, we are not so lucky, always so lucky, and oops, sometimes we won't find a match at all. In this case, the solution for LZ77 is to output a literal byte, which is the A in this case. and then move forward 1 byte. To improve the performance of LZ77, we will use the hash table to assist the lookup. By using a few bytes from the hide window to calculate the hash value and indexing the hash table, you can find out where the potential match is in the history window. Then we just need to match along these candidates. We refer to a row in the hash table as a hash row. Keep this in your mind and we will mention it a lot later. After the matching is complete, don't forget to insert the corresponding position in the head window into the hash row as well. This is necessary because the hash table is built incrementally as the data is moved in. As you can see, the control flow of LZ77 is heavily data dependent. So what about a parallel version of LZ77? Let me review a common idea in previous studies. Firstly, we need to compute the hash value in parallel. Multiple input positions here are 3 are taken into consideration and we get 3 hash values. Then the hash table should also support parallel exercise, thus taking out 3 hash rows in the same cycle. Next, the output hash rows are sent to an array of match PE. Each match PE keeps a copy of the sliding window, and the 3 match operations take place in match PE finally. By now, I believe you have some basic understanding of compression algorithms. Let's talk about our design. Our challenge. The first challenge comes from the large sliding window. For a better compression ratio, this standard requires a sliding window larger than before. The expansion of sliding window leads to more on-chip memory results in both the hash table and the match PE. And here, let's just wave the match PE. Suppose we have 64 match PEs, an ideal choice according to our exploration, and each PE keeps a copy of the sliding window. When we want a 2 megabit sliding window, the S/B match PE alone require 128 megabytes. That doesn't sound good. The logic of this challenge is that we want the sliding window to be as large as possible, but not for the on-chip memory. I'd like to add a clarification here that the sliding window size we end up spotting is the middle one, 512 kilobytes. But we only need a total of 18 megabits of on-chip memory, which is less than the 32 listed here. The second challenge comes from the irregular control flow. The hash operation and the substring match operations have data dependency. On the on, profiling results from one API we tune shows that bad speculations waste about 30% of the pipeline slots. When this phenomenon is reflected on the accelerator, it becomes a contention for hardware results or a waste of ideal ones. We define it as a parallel conflict. The 2 challenges motivate us to an organized compression architecture. We should avoid unorganized design patterns like massive and redundant parallel operations or lack of proper scheduling. Unorganized architecture with low redundancy and lower parallelism is what we're looking forward to. Now it's time to show our design. We start our design with a new algorithm. The first stage, parallel hash access, is no different from the way it used to be. H bytes in, H rows out. Just for the convenience of the later discussion, we named it B-hashi. Then things get interesting. Instead of directly assign several match PEs to each hash row, we pack multiple hash rows into a match job in the sequence of outputs. Next, we take match jobs as our parallel granularity. The half match part of algorithm takes multiple match jobs in parallel. This is a novel parallelism design. In each match job, hash rows are proceeded in serial. The advantage of this serial miner is clear. We can skip redundant operations as we want. So this is a low redundancy design. Corresponding to the algorithm, the BeeZip system is mainly comprised by 2 hardware engines, B-hash engine and half match engine. Uncompressed input streams into the system, and we can get a compressed output stream on the other side. The 2 hardware accelerators are connected to the standard external producer API. It's an offload interface provided by this standard. In the B-hash engine, multiple hash PE together form a hash table that can access in parallel. An interconnect component is required between the hash function unit and hash PE. We upgrade the interconnect structure into two schedulers that work together, pre and post one, for dynamic scheduling. The scheduling strategy can be summarized as do your best. Each hash PE tries to handle requests as much as possible, but wouldn't wait too long and give up some requests if there was too much operations. The exact wait time is determined by a runtime configurable parameter HQT. Configuration of HQT enable BeeZip's trade-off between compression ratio and throughput. This is the novel parallelism design that attempts to mitigate the irregular control flow. As for the how match engine, we explore the multi-level parallelism to align with the algorithm. Inter-PE coordinators receive hash rows from the B hash engine and pack them into match job. Then the match job are sent to match PE in a round-robin manner. Multiple match jobs are proceed at the same time among all match PE. In the match PE, there are the intra-PE coordinator and a group of match PO. The intra-PE coordinators send out the hash rows of the match job serially. Each hash row is handled by all match PE concurrently. This is a novel parallelism design. In the intra-PE coordinator has an internal table to track match job processing. The match PO, on the other hand, is a pipeline structure that accomplishes stream matching operations. It has to hold the sliding window in the SRAM buffer. The final key design is a heterogeneous scope PO. The size of each match PO is not the same. We only provide one match PO that keeps a complete sliding window. The other match PO is relatively small and only holds the near part of the sliding window. The intra-PE coordinators keeps the size of match PO in mind and send the request respectively. This is a low redundancy design. Now let's combine this design and come to experimental results. We take Silicea Corps as the general proposed lossless compression benchmark. Software baseline Z standard on a server with 2 Xeon Gold CPU. Another 7 accelerator designs, Core GPU, FPGA, ASIC taken in consideration. This covers the project zipline, CDPU, and on. We implement the B hash and how match engine in Verilog, run the simulation successfully, senses to 1 GHz on a 14 nanometer process node. Here is the overall performance. The 3 results points correspond to 3 BeeZip models by config different HQT. Let's dissect the results in a summary. Yeah, BeeZip combines the advantages of software and the existing accelerators. It has a 23.2 or 2.45 times higher throughput than the single or multi-threaded software on the CPU, and at least a 9% higher compression ratio than accelerators at accelerator baselines. Since the current air power consumption results for the BeeZip comes from logic senses and the favor baseline provide such information, it may not be fair to make a quantitatively comparisons. From a qualitative comparison point of view, BeeZip can be a practical accelerator in our mind, and the more precise results will need to be obtained through future prototyping. Several other experiments demonstrate the effectiveness of our design. Due to the time constraints, we refer you to our paper for further details. Here I give a summary and a point of our future work. BeeZip is an organized and scalable data compression architecture. A novel algorithm and accelerator are proposed. The experimental results show that BeeZip achieves a balanced increase in compression ratio and support at the standard. It's combined advantage of existing software and accelerators. For the future work, we are now working on porting BeeZip to an FPGA accelerator card. We also like to add a hardware entropy encoder for the end-to-end standard compression. BeeZip is open source, and we are excited to team up with you. Thanks, and any questions? Okay, thanks.
Hey, thank you for the talk and thank you for doing the open source. So I have one question. So I think if I remember correctly in the previous work in CDPU, they pointing out that the compression accelerator should be as close as to the CPU. So have you guys considered like mechanism to like couple this accelerator closely with the CPU?
Okay, I think it's okay to compress the accelerator to the CPU, but similarly, I don't much agree that because our compression accelerator is used to process data of big volume, it should works in a stream manner, big data stream in the accelerator and then stream out. If we close it to CPU, maybe the cache hierarchy will comply. So, but for the CDPU, you mentioned it is used for Google Data Center. To handle small file distribution or just compress a small request or query from the user. It's okay to tightly coupled with the CPU.
I see. Thank you.
Thank you.
Okay. Thank
Okay.
you.
Okay.
Yes.
So hello everyone, I'm Junseo Lee from Seoul National University. Today, I'm going to present our work, GSCore Efficient Radiance Field Rendering via Architecture Support for 3D Gaussian Splatting. So what is 3D Gaussian Splatting? It is an emerging technique that generates photorealistic images using a set of Gaussians. To do so, we begin by capturing photos of the space from various viewpoints. Then, by using these photos, we can generate a 3D Gaussian model that represents the space. After the training, we can render photorealistic images from any viewpoint. Now, let me talk about the rendering process. When a novel viewpoint is given, we first project the Gaussian onto an image plane. This process is called splatting, and the projected Gaussian are called 2D splats. And then we sort the Gaussians by the depth value and accumulate the colors from the closest one. While it shows state-of-the-art rendering performance, it is still slow on an edge device. And in detail, sorting and rasterization are two main bottlenecks, which take more than 80% of the total rendering time. This is the outline of today's talk. I will first explain GPU optimization of 3D Gaussian splatting and its inefficiency. Then we propose our solution, GSCore, an efficient radiance field rendering accelerator. Finally, I will show our evaluation and end with a conclusion. 3D Gaussian splatting employs tile-based rasterization to increase the rendering performance. The key idea is to divide an image into multiple tiles and render each tile by using only a small set of Gaussians. To do so, we first draw a square with a circle surrounding the splat. This square is called an axis-aligned bounding box. Then, the splits are assigned to the tiles that the bounding box intersects. After the tile assignments, we first compute the depth values of the Gaussians, each of which indicates the distance between the viewpoint and the Gaussian. Then, the Gaussian are sorted by the depth values. And finally, the tile is mapped to a GPU thread block and render colors in parallel. While it is optimized for GPU rendering, we found three inefficiencies in this process. The first is that the original algorithms lead to unnecessary assignment of Gaussians to tiles. So in this example, there are many tiles that are marked as intersected, even though they are not. As a result, unnecessary tile assignments increase the work overhead of sorting and rasterization. The second problem is ineffective alpha computation within a tile. So because of tile-based execution, all the threads in the tile work on the same Gaussian, even though only a few pixels are within the splat. In this figure, almost 90% of the thread do ineffective alpha computation. Considering alpha computations requires an expensive exponential operation with multiple floating point operations, the ineffective computations occupies a large portion of the execution time. Third, the original implementations sourced the entire Gaussians before the rasterization. In the rasterization stage, we stop the rendering when we meet the Gaussians that represent the surface. This is called early termination. The last problem is that there is unnecessary sorting overhead for the Gaussians that will not be used. To mitigate these three problems, we propose GSCore, an efficient radiance field rendering accelerator with an algorithm hardware co-design. To solve the first problems of 3D Gaussian splatting, we propose Gaussian shape-aware intersection test. While the original AABB-based intersection test is computationally cheap, it leads to a large gap between the splat and a bounding box. Instead, our method proposed a tighter bounding box, and it effectively reduced this gap. And also, as this kind of intersection test requires more computations, we opportunistically apply this method only for highly skewed Gaussians. By using this optimization, we can effectively reduce the number of tile assignments. In this example, our method reduces the number by more than 2 times without any approximations. As a result, the shape-aware intersection test effectively reduced sorting and rasterization overhead. To mitigate the second problems of the original implementation, we propose subtile skipping. The key insight is that since we actually know the exact boundary of the splat, we can figure out which pixels will use the Gaussian before the rasterization. So our key idea is to divide each tile into smaller sections, which we call subtiles. Then in the pre-processing time, we generate a subtile bitmap that indicates whether the splat intersects the subtiles. By using this information in the rasterization stage, we can skip the subtiles when the corresponding bit is 0. As a result, we can effectively reduce the rasterization time by avoiding unnecessary alpha computation. Finally, we solve the last problem of the original implementation. We propose hierarchical sorting. After we compute the depth values of the Gaussians, as shown in the boxes, the original implementation sorts the entire splat before the rasterization. However, if only half of the Gaussians are used and the rendering is terminated, it turns out that the rest of the Gaussians are unnecessarily sorted. To mitigate this problem, we propose a 2-stage sorting process. In the first stage, we approximately sort the Gaussians into multiple groups, ensuring that the lower group always have the lower depth values. Please note that the Gaussians in the same group are not actually sorted. So in the second stage, we precisely sort the Gaussian within the same group and start the rasterization. By using this method, if the rendering is terminated using only a first few groups, we can skip precise sorting of the next groups. This optimization provides 2 key benefits. The first is that it reduces sorting overhead for the Gaussians that will not be used. And the second advantage is that it enables parallel execution of the sorting and rasterization, so we can hide the precise sorting latency. To efficiently support these optimizations, we propose GSCore, a novel rendering acceleration unit. In GSCore, there are 3 main hardware units, but in the interest of time, I will focus on the volume rendering unit. The volume rendering unit is responsible for doing rasterization. In the VRU, there are multiple VR cores and on-chip buffers. To increase the benefit of subtile skipping, the VRU renders the pixels in a subtile granularity. So each VR core computes the alpha value of the Gaussian and uses it to update the transmittance value. In the transmittance equation, there is a dependency between 2 consecutive transmittance values. As our architecture is fully pipelined and it requires a floating point multiply and accumulate operation, it leads to a pipeline stall to resolve this dependency. To mitigate this problem, we propose pixel rotating pipelining. Since there are no data dependency between the transmittance of different pixels, the VR core keeps working on other pixels without any stall. Now we present our evaluation. So this is the methodology of our work. We implement the hardware component in RTL and shows 1% area overhead compared to the edge GPU. For performance evaluation, we also implement a cycle level simulator with functionality model. We carefully choose 4 different data sets to cover both synthetic and real-world scenes. First, we'll present performance. In this figure, the x-axis is different data set and the y-axis is in speed up. Since our algorithmic optimization reduces ineffective computation, it leads to about a 2x speed up over the original implementation. And with the hardware support, GSCore achieves about a 16x speed up over the GPU. In detail, I will show the speed up when applying our algorithmic optimization incrementally. So the baseline is the original implementation in GSCore. First, shape-aware intersection test reduces falsely assigned Gaussians, and it leads to about a 1.9x speedup. Second, subtile skipping reduces ineffective alpha computation and further achieves an additional 16% speedup. Hierarchical sorting reduces unnecessary sorting overhead and hides the sorting latency. So finally, GSCore achieves about a 2.4x speedup over the baseline. As a result, GSCore enables real-time rendering with a substantially small area overhead. We discuss more results in our papers, such as roofline modeling and discussion about using RT cores for intersection tests. So please check out our paper for more details. To conclude, we propose GSCore, an efficient Radiance field rendering unit with an algorithm hardware co-design. As a result, GSCore achieves about a 16x speedup over the GPU with a substantially small area overhead. So this is the end of my talk, and thank you for listening.
No questions?
What do you anticipate the using the RT cores to buy you in terms of performance? And have you thought about using the RT cores, and what kind of instructions would you need in the GPU cores to do the rest of it?
So this is a good question, and your question about using RT cores for intersection tests in the 3D Gaussian splatting.
Yeah.
So my answer is it can't be used in the rendering, but we expect that when we use RT cores for intersection tests is kind of expensive compared to the original rasterization method, because After rasterization, the Gaussian is projected to 2D ellipses, but in the 3D space, the bounding box is more larger than in the 2D space. So it also leads to more false positive of intersected voxels. So I think it can be, but it's not that beneficial compared to the original implementation. So also the latter question is about how we extend the GPU to support the rasterization.
Yeah.
And the answer is we can't do by adding some instruction to do blending operation for color and some other operation to do rest of the alpha computation, especially exponential operation. So if we extend that kinds of instruction in the GPU, we can do the rasterization using RT-Core and GPU.
Thank you.
All right, let's thank the speaker once more. All right, our fourth presenter is Shaojun. Shaojun is a final year PhD candidate in the CS department at the Illinois Institute of Technology. His research interests include performance modeling, cache memory performance optimization, AI-assisted computer architecture design, and hardware and systems for machine learning.
Thank you, Chair. Hello, everyone. I'm Shaojun from Illinois Institute of Technology. So I'm very happy to be here to share our work, ASIS, accelerating sparse matrix multiplication with adaptive execution flow and concurrency-aware cache optimizations. So this work aims to enhance the sparse matrix multiplication, SPMM. So that is essential for various sparse algorithms, such as those in sparse neural networks, sparse linear algebra, and tensor algebra. So there is an increasing demand for higher performance and efficiency in SPMM. Sparse matrices usually have various sizes, so densities, and distribution of non-zeros, so which significant challenges for traditional cache-based architectures, so which are typically optimized for dense or regular data patterns. And we found that there are three common limitations for current SPMM accelerators. So the first limitation is the fixed execution flow. So the execution flows of SPMM can determine how the matrices are processed. The modern SPMM accelerators, so mostly based on a fixed execution flow. So the three execution flows, so which are usually used in SPMM, it's inter product, so outer product, and row by row. However, so each execution flow has different characteristics in terms of input and output data reuse, index intersection efficiency, and synchronization requirements. So in fact, a fixed execution flow may provide inconsistent performance across different sparse patterns. Therefore, adaptive execution flow is needed. Furthermore, the conventional cache replacement policies used in SPMM accelerators aim to reduce the number of the cache misses, but overlook the importance of concurrency. So in SPMM, it is common to require cache lines of a row or column concurrently. So this concurrency means that even a single cache miss can cause delays in the whole processing chain. And moreover, the cache design in current accelerators does not incorporate the non-blocking features. So as a result, a single cache miss causes delays in subsequent accesses. Therefore, an efficient accelerator should be designed to handle the concurrent access demands of SPMM and ensuring the non-blocking cache operations to optimize the overall performance of the accelerator. And to solve these challenges of traditional SPMM accelerators, we designed ASIS with 3 important components. So condensing adapter, the pure fiber catch replacement policy, and the NB buffer to provide adaptive execution flow and global on-chip catch optimizations. So first, we dynamically tune the condensed matrix representation for matrix A to implement the adaptive execution flow. So in figure A, it shows a normal sparse matrix where no condensing is applied to matrix A. And the figure B, it shows aggressive condensing for matrix A involves shifting all the non-zero elements to the leftmost columns. And in figure C shows a moderate condensing. So the columns of the matrix A are divided into 2 groups, the first half in one group and the second half in another. Within each group, the non-zero elements of matrix A are shifted to the leftmost columns. So we observe that different condensing degree can impact the execution flow of SPMM. For example, consider there are 4 processing elements. So each processing 1 scalar vector multiplication, and each element that is scalar is come from the matrix A, and it's multiplied with the corresponding row, the vector of the matrix B. So we can observe that the different condensing degree can provide various execution flows. Therefore, it is critical to determine the execution flow by choosing the optimal condensing degree in response to different sparse patterns. In order to achieve adaptive execution flow, we must first detect the sparse patterns and then select the condensing degrees. So for detecting the sparse patterns inspired by Sparta, so we reorganize that adjacent rows with a similar distribution of non-zero elements. So based on these observations, we can partition the rows into the bands. So based on the change in the row length at runtime. So with rows in the same band shows similar sparse patterns. Next, we have to select optimal condensing degree for each band. So for a large band, we determine the optimal condensing degree through a sampling phase. So this involves running 3 sampling phases. So each pass testing a different condensing degree, and then select the degree that shows the highest performance for the subsequent rows within the band. So for the small band, we just bypass the sampling phase and apply a moderate condensing degree directly. Once the condensing degree of matrix A is determined, so we can know the demands order of the rows in the matrix B. So therefore, we can calculate the next reuse distance, RD, to dynamically capture the reuse distance to the rows, so which indicates the expected time until the row is next request. So giving us the information about the data locality. So in addition to the locality information, so we also observe that when multiplying an element from matrix A, so with the elements from the corresponding row to the matrix B, so leads to the concurrent requests for the catch lines of the matrix B. So that means a single catch miss among these requests can stall the scalar vector multiplication process. So we use the fiber density FD to capture the number of the catch lines in the corresponding row. So serving as an indicator of potential concurrent exercises. We developed the pure fiber, that is a concurrency-aware catch replacement policy. So we define the pure fiber as a scenario where the catch lines of row are accessed concurrently without any catch misses. So achieving a high number of the pure fibers in SPMM is critical to mitigate the total cache loss. So when making eviction direct policy to make decisions for the cache line eviction for the on-chip cache, so the pure fiber policy just select the cache line with the highest combined sum of the FD and the RD for eviction. So finally, the ASIS incorporates a non-blocking buffer, NB buffer, that manages the concurrent cache miss accesses. So when a miss occurs in the global cache, so rather than storing like a traditional blocking cache would, we record the miss information in the NB buffer. So the NB buffer then fetches missing data from the main memory. The NB buffer can handle the multiple outstanding cache requests concurrently, so allowing the global cache to issue the new memory requests even when the previous ones are still being serviced. We evaluate the performance of the ASIS using the sweet sparse matrix collection. We select 3 state-of-art SPMM accelerators, Sigma, SPARC, and Spada for performance comparisons. ASIS is organized with 16 MPEs, 16 APEs, 1 MB global cache, and 0.5 KB MB buffer. The area overhead of ASIS is 3.5 square millimeters, and it requires a total of 2.8 watts of power. We evaluate the ASIS against 3 state-of-the-art SPMM accelerators among various workloads. Overall, the ASIS consistently provides the optimal performance across all the workloads, and with average speed up of 25.5 times over Sigma, 8.9 times over SPARC, and 2.1 times over Spada. To evaluate the effectiveness of the pure fiber cache replacement policy, we introduced a simpler version of ASIS. So at ASIS LRU, which uses LRU as the global cache replacement policy. And ASIS with the pure fiber policy to achieve an average improvement of 15.9% over the LRU baseline. To showcase the effectiveness of integrating an NB buffer with the global cache in ASIS, we compare its performance to that of another version of ASIS that without integrating the NB buffer. So we show that with the help of a non-blocking buffer, the ASIS achieves 35.8% of speedup. In summary, we designed a SPMM accelerator ASIS. So ASIS features an adaptive execution data locality and concurrent data access demands for replacement decisions. And ASIS also integrates a non-blocking buffer with the global cache to enhance the concurrency with reduce the loss. And finally, the ASIS outperforms state-of-art SPMM accelerators. Thank you. So that is the QR code. If you are interested in our paper, you can scan that. Thank you.
Have you thought about what the overhead would be when you combine this with a dense matrix multiply engine? And I'm wondering more specifically if you could speculate on what it would take in terms of overhead to combine this with one of the AI accelerators that we're increasingly seeing.
Yeah, so we consider the overhead. For example, if we combine the non-blocking buffer with the on-chip cache, and we found that we can reduce some size of the on-chip cache and use that kind of size to the on-chip buffer, non-blocking buffer. to provide the concurrent data accesses. So that kind of concurrency is worth. So, and we can, for example, if we have 1.5 MB total on-chip, let's say overhead or storage overhead, we can use some point of them to be a MB buffer to another kind of cache to handle the concurrent data access and reduce the total on-chip cache capacity. So the total capacity may be the same, but we're just using some other storage for the MB buffer. So we do not. Yeah.
Thank you.
Thank you.
Okay, thanks again. All right, our final talk of this session is from Shail Dave. Shail is a final year PhD candidate at Arizona State University. His research techniques and infrastructure enable efficient processing of critical applications like machine learning on hardware accelerators in an agile manner. His research covers architectural modeling and characterization of domain-specific architectures, loop-level compiler optimizations, and hardware-software co-design. His works have been featured in several technical media as well as industrial forums. Yeah, whenever you're ready.
Hi, everyone. Thanks for attending the session, and thank you for the introduction. So I'm Shail from Arizona State University, and this is joint work with Professor Tony Nowacki at UCLA and this work is done under the Semiconductor Research Corporation AI Hardware Program. So this work is about how do we make design space exploration more efficient and explainable by using bottleneck analysis. Design space exploration is important step in achieving efficient architecture designs, right? Which is important for a smooth user experience, and it needs to meet like several execution constraints so that there could be smooth user experience and low cost designs. So now, particularly for machine learning workloads, this design space exploration is challenging because the search space is very vast. For example, if we consider HTPU or Iris chip from MIT or any other accelerator architecture templates, there could be like 10 to the power of 14 or 20 hardware configurations. And for each of the hardware configuration right now, there needs to be mapping of one or more machine learning workloads, right? So each actually ML or DL model, each layer of that, mapping that also takes like about 10 to the power 20 or higher configurations. So individual search spaces are vast and collective search space is even vast for hardware software co-design. So actually existing techniques to achieve efficient configurations, design configurations, they apply this black box optimization techniques. So for example, genetic algorithm, simulated annealing, Bayesian optimization, reinforcement learning, right? And all these techniques, what they do is that they would actually make some sample into the search space for some configuration. For example, say hardware configuration, and then they would evaluate the system which is containing the cost model or the simulator, right? And it would give the power performance area matrix. And now that basically, and then there is a total cost value, right? So then it is using only that total cost value to predict where, I should be sampling next. So for example, if we take this tiny toy example here, right, it is showing two hardware parameters like number of processing element and shared buffer size. This diagram here is showing actually efficiency for running some ResNet layer, and this optimizer is a hypermapper, which is basically a very efficient Bayesian optimization tool. So what happens is that initially it is making some samples here in this dark region, which is low efficiency region. And then eventually it is finding out some solutions in, this shaded, light shaded region, which is some efficient solution. But even then, in subsequent samples, it would still surge into again this dark region, which is high cost region, right? And the reason is that there is no, whenever the samples are happening, there is no reasoning about efficiency of the obtained solution, that it's just taking the total cost. It is not really looking under the hood that why this configuration is giving me this cost, and what are the inefficiencies within that, and how should I mitigate those, right? I mean, what should be my next samples that could actually address these inefficiencies. So result is that actually there is pretty less search budget, like several thousands of trials. But even then it would take like many days or weeks, and it would actually find maybe infeasible or at least inefficient solutions. So how do we address this? So idea is that let's use bottleneck analysis or root cause analysis. So if I consider this tiny space, right, if I'm starting with this minimal configuration, right, which is 64 processing element and 64 kilobyte of shared buffer. Now, if I evaluate this point as a designer, and if I know that, hey, my computation time is actually the challenge, because this is a very a tiny accelerator point. So maybe I can try to increase the processing element. And if I get to know that eventually my off-chip access is becoming the bottleneck, I should be increasing the off-chip bandwidth, or maybe provision more on-chip buffer, right, to do more reuse. So then I can mitigate that. And then next, maybe some point of time, again, computation becomes the bottleneck for just this 2 parameter search space here. And so eventually I can lead to, optimal solution region. So this bottleneck analysis is actually classical concept, right? But the challenge here is that how do I expose this information, that what is the bottleneck, what is the related factors here, right? This computation time, communication time, and under the hood calculation. How do I expose this information? That's the main challenge. And that also for variety of accelerators or workloads. Right. So the idea is that so one thing is that actually all this information is available in your cost model, like the cost model or simulator. They are containing thousands of lines of code. They have all this information available, but it is not explicit or analyzable. Right. It is under your cost model, which is giving finally some cost value at the end. So now the idea here is to introduce, like develop and use the bottleneck model, which is essentially graph version of the cost model. So what it is doing is that it is this bottleneck model, the root of the node, it's actually this graph or a tree, where root of the tree is the end metric, like total latency. And the leaf nodes are my final hardware or software parameters, for example, number of compute elements, or the basically off-chip bandwidth, or number of the links within the interconnects, types of the interconnects, type of the compute element, and so on and so forth. And software parameters are like your tiling or ordering of the loop, which is translating to number of tensors that you are communicating, the work group that you are partitioning for on-chip resources, right? So that execution or information, and maybe quantization or the bit width, right, of the data operands. So that software information is there. So now, just like your cost model calculation, this graph is taking this hardware and software parameters into the account and formulating this intermediate computation with this mathematical operation like add, max, ceiling operation, floor operation, anyhow, like how exactly your cost model would calculate your calculation, but this is in the graph form now, and this graph is actually analyzable and traversable, right? So now what happens is that I have this graph, which is now giving me information about how my latency is getting calculated from this hardware and software parameters. And so now when I run, let's say I have a sample efficient solution, right, with me, or some solution found at some design step. So now when I run some operator, right, for example, some jam operator or convolution operator or whatever ML model layer, right, onto some sample configuration, now values would be popping up, right, for that bottleneck model graph. And now what can happen is that I can analyze this graph, right, for that best solution I obtained so far. So for example, my total latency here is 1 million cycles, right? And it is coming from maximum of 3 values, which is your on-chip computation time, on-chip communication time, and off-chip memory access time. So now looking at this graph, now actually it can traverse and it can pinpoint that, hey, my network on-chip network time is actually the bottleneck. It's not really hiding the communication time well. This design is not hiding the communication time well. And network 1 is actually maybe processing certain tensor, and that is how it is generating this 1 million cycles. So now, and by pinpointing to underlying hardware or software parameters, now you can pop up 3 solutions that, okay, one solution is maybe this is actually like unicast kind of communication pattern, but I have provisioned only one link. There is no unicast network here. Maybe I should increase more on-chip links to provide more, on-chip bandwidth. Or maybe I should increase the data bit width by a certain factor. Or maybe I should increase the on-chip buffer size so that I could provision more data reuse on chip, right? So that maybe there is less access is needed for the network. So, so now actually we had a design point at certain point, and then now there are 3 options. So we can actually try each of them and evaluate and pick which one is the best. And we could do this iteratively, right? So that we could keep addressing the bottleneck. But there are more things to do. Typically, there are this multiple ML workloads I need to find the best solution for. And then each workload has many ML layers, I mean, many layers, right? For example, and for each layer, now there is a different bottleneck. So bottleneck are very diverse, right? For different workloads and many layers. So one thing is that I need to focus on only top performance critical layers so that I can narrow down my mitigation that I need to try. And second is that for any parameter, there might be many values possible. So I need to aggregate that in some way. So for example, there are 2 or 5 possible values for, let's say, network bit width. So maybe I am going to take the minimum across those distant values so that I really don't converge fast, but I can still cover the interesting design points in between, right? So essentially, all I'm saying is that there are sort of aggregation that you need to make across your prediction so that you can consider all these bottlenecks across all your workloads and all your layers in these ML models. And there is also constraint awareness need to be there. So typically what this black box algorithms do is that they don't really try to find the solution, which is, even if your constraints are not met, it keep reducing objective. But what we do is that we consider average budget of the constraints. So we first try to find the solution that is meeting constraints the most. And if many solutions are valid, then it would try to find the one that that is reducing objective, but not exhausting the constraint budget. So we evaluated this on edge deep learning accelerator setup for this different black box techniques. We use performance constraints from MLPerf and Iris, HTPU, Intel and ARM chips for power area budgets. And we considered both the fixed data flow as well as hardware software co-design search. And the results show that we can find this bottleneck analysis driven exploration could achieve 6 times low latency solution. And that also very quickly, like in 36 times low search time, which is minutes or hours as compared to many days or weeks. So this is the search time reduction in this bottom graph, and this first one shows the performance improvement. And the result is that it is actually converging pretty fast. So you can see that actually this is converging in like 50 or 100 trials in this log scale compared to 5,000 trials or 2,500 trials, right? So it is actually mitigating bottleneck at every iteration or every step. So it is converging fast, and compared to black box techniques, that is like really barely improving solution across thousands of trials. So that is the main reason behind this. And yeah, so to conclude, this black box exploration techniques really cannot pinpoint to the underlying inefficiencies into the execution. So we need to use bottleneck analysis in some way. And to make that bottleneck characterization of cost possible, we introduce bottleneck models and a programmable API so that this bottleneck analysis can be done systematically. And this is done for multiple workload running under constraints. And it can find very efficient solutions quickly, like hours or minutes, compared to many days or weeks. Thank you for your attention, and I'm looking forward to any questions. Thank you so much.
Hello, this is Gerasimus from UC. Great work. I'm supposing that your work always needs an analytical model that correlates the design parameters with the expected bottlenecks. We can't have something like that for all the accelerators, but it would be nice to introduce the insight of associating bottlenecks with design space explorations in such accelerators as well. What are your thoughts about applying this to accelerators without easily constructible cost models?
Right, a great question. So I think the question is that for a variety of accelerators, how this bottleneck models could be introduced, right? I think if I understand it correctly.
Sorry, could you repeat?
Huh?
Could you repeat?
Yeah, I mean, how could we introduce bottleneck models for variety of accelerators, right?
Right, for some accelerators, we don't have right now, or it might be very difficult to construct.
Yes, the more automation for this. Yes. So I think the idea is that this bottleneck models are not new analytical model. They are taking the existing cost model, right? So there are few ways this can be done. One is that there are libraries that are implementing the cost functions, right, for the parts of the accelerators. So we could also just import a graph module like, hey, this is the graph representation for this component, right? So whenever you are aggregating for your accelerator components, you could construct that graph automatically, but that is coming from the designer. Other ways that maybe I don't know, some sort of automation tool like some graph parser or maybe even ChatGPT that, hey, this is my mathematical, arithmetic that it is doing this divided by this. What is the graph form of this, right, in this file format? So yes, I don't have that automation tool, but I think that's kind of, there are this kind of ways I think we are considering to enable this to broader set of designs. Thank you so much.
Nice work. Eric Liang from Peking University. So I'm wondering how to extend your technique to a multi-objective design space exploration. For example, I want to derive the Pareto optimal curve.
For the Pareto optimality, right? Yeah, great question. So I think, yeah, this is mainly for single objective search. But I think for Pareto optimal solutions, what we could do is that probably we could have, we could apply the standard techniques where actually there would be search going on for each of the cost metric in parallel as a separate boxes, right? Populating to each of the curves. So there needs to be bottleneck analysis for each of the, like, for example, for the power graph, for the performance graph, there needs to be bottleneck model and driving the search engines in parallel for all the, cost in my multi-objective search, I think so. Thank you.
Okay, that concludes this session. Thank you all for coming. Thanks.
Thank you. Thank you. Thank you.